For today's pre-lecture video, I'm going to go over an example with using Coulomb's law and talk a little bit about that. One of the importances of what I want to cover in this pre-lecture video is a review of how we add vectors, a skill you should have learned in the first semester of physics, but might be a little rusty since you haven't done it for a while. So in Coulomb's law, what we're describing is the force between two charges. So I have Q1 and Q2, and they're separated by some distance r. According to Coulomb's law, the force that exists between the two is equal to a constant, it's the Coulomb constant, times the product of the two charges divided by the distance squared. And the Coulomb constant is equal to 8.99 times 10 to the 9th. And that would be Newton meter squared per Coulomb squared. So you might notice that this force looks a lot like the force of gravity, which was equal to big G m1 m2 over r squared. And it does have a very similar appearance. It's a similar sort of way that it works. Both of these are inverse square laws. They both depend on a product of the quantities that are of interest to us. For Coulomb's law, we're interested in the charge, where for gravitation, we're interested in the mass. And finally, they both have some constant of proportionality. If you remember, the constant of proportionality for gravity was a very small number, 6.67 times 10 to the minus 11, where we see the Coulomb constant is actually a much larger value, which makes this a much stronger force. So the force between two charges is actually much stronger than the force of gravity, which would be the force of attraction between two masses. And when I said attraction, that reminded me of another way that these two force laws are different. It actually ends up that when we're talking about the force between two charges, the force could actually be attractive or repulsive depending on the sign of the two charges. Because what we find, according to Coulomb's law, is that like charges repel, so that means two positive or two negative charges, while opposite charges will attract. Where when we talked about the force of gravity, there was only a force of attraction. All right, so like I said in the previous example, if I have two charges, like a positive charge and a negative charge, when I'm talking about the force between these two charges, there's actually a force of attraction because opposites attract, where if I had two positive charges or two negative charges that were close together, these forces would actually exert repulsive forces on each other. And so that's another important thing that we need to remember. So when I'm talking about the force between two charges, like let's say I have two positive charges which are going to repel each other with some force, the force is the same for both charges because of the fact that it's an action-reaction pair. And I'm calculating the magnitude of the force kq times q over r squared. I would leave these two positive, but even if I had two negative signs that had a magnitude of q, when I was finding the magnitude of the force, I would still just put the magnitude of the charge and I wouldn't put in the negative signs because I've already taken into account the negative sign when I showed the direction of the vector. So when I drew the vector for the force, I was already indicating in this case that the two charges would repel each other. Similarly, if I had a positive and a negative charge, I would draw the forces like this. And again, if I would calculate the force of attraction between the two, I wouldn't make one of the Q's negative and one positive. I've already taken those two different charges into account when I drew the forces as attractive. And that's something that sometimes we forget when we're doing a calculation, is that, like, if we're adding the total force acting on a charge, we draw the arrow to represent the direction of the force using the sign of the two charges that we're looking at. And so once I've done that and drawn the direction of that vector, I don't need to use the sign of the charge again. Now I just need to know how big is that force. So I only will use the magnitude of the charge. Then once I have drawn my forces, so let's say I have a triangle, Q1, Q2, and Q3, if I had three charges on the vertices of a triangle, and I drew the forces acting on the top charge, I'm going to call this one F2 and this one F3, and I wanted to find the total force, the way that I do that is I actually will find the x component of each vector, add them together. I will find the y component of each vector and add them together. And then find the magnitude using the Pythagorean theorem. And finally, I would find the angle that the total vector would point at using the inverse tangent. And so once I've done sort of finding the direction of the forces and how large the force is, all this should look like review, because this is simply adding vectors, and that's something that we've done in the previous semester. So I'm going to look at an example to show you how we would go about doing this, to give you some refreshing. So I'm going to say that I have a rectangle, and on the rectangle I have 4 charges. I'm going to call this one Q1, which is going to be equal to -2 microcoulombs. At this corner, I'm going to have Q2, which is a 3 microcoulomb charge. Here I have Q3, which is -5 microcoulombs. And here is Q4, which is 6 microcoulombs. The dimensions of this rectangle are the short side is 3 meters and the long side is 4 meters. And I want to find the total force on Q4 due to the other 3 charges. So this is going to be sort of a typical type of problem that I might deal with when I'm using a combination of Coulomb's law and adding vectors. So what I'm going to do is, the first thing I'm going to do is I'm going to find the force acting on Q4 from each of the 3 charges, and I'm going to draw a vector representing the direction of that force. When I think about Q1, Q1 is negative, but Q4 is positive, so these forces are going to attract. So the direction of the force due to 1 is going to be towards charge 1. When I look at the force due to charge 2, though charge 2 and charge 4 are actually both positively signed, so they repel each other. So the force that 2 exerts on 4 is going to be a repulsive force, so it'll be straight up. And then finally, charge number 3 will attract charge number 4 because they're an opposite sign, so F3 will be in this direction. So now I've drawn the 3 directions of the forces. Now I have to see how big they are. So F1 is going to be equal to K Q1 Q4 over the distance between 1 and 4 squared. So that's 8.99 times 10 to the 9th. Now, do you remember what a microcoulomb is? It's 10 to the minus 6. So I have 2 times 10 to the minus 6 times 6 times 10 to the minus 6 and divided by, now this is actually going to form a 3, 4, 5 triangle, and so the diagonal of this rectangle is going to be 5 meters. When I do the calculation, this ends up to be 4.3 times 10 to the minus 3 newtons. Force 2 is equal to K Q2 Q4, and then the distance between 2 and 4 squared. And the distance between them is 3. That force is a little larger because the charges are a little larger and the distance is a little smaller. Finally, the force of 3 on number 4 is 8.99 times 10 to the 9th. 5 times 10 to the minus 6 and 6 times 10 to the minus 6, and the distance between them is 4 squared, and that gives me 1.69 times 10 to the minus 2 newtons. Alright, so we have found all of the 3 forces. That's the magnitude of them. Remember, I have this picture to remind me of what they look like, what the direction looks like. So I'm gonna go to the next slide, and I'm just gonna draw the vectors really quickly again. This is 1, 2, 3, 4, and then the direction of the vectors. This was F1, this was F2, and this was F3. So when I want to find all the x components, oh, and one of the things I'm going to need to know is this angle. And I did do the trig, and this is 36.9 degrees, just so we know. Okay, now for the x component, I have minus F3 minus F1 times the cosine of 36.9 degrees. Because F3 points to the left, and so does F1 has a negative x component as well. So that's going to be minus 1.69 times 10 to the minus 2 minus 4.3 times 10 to the minus 3 times the cosine of 36.9. So the x component ends up to be a negative x component, not a surprise, times 10 to the minus 2. When I look at the y components, I'm going to have F2 minus F1 sine of 36.9 degrees. F2 is 1.8 times 10 to the minus 2 minus 4.3 times 10 to the minus 3 sine of 36.9 degrees. My y component turns out to be 1.54 times 10 to the minus 2 newtons. My total magnitude of the force, the magnitude of the total force, is found by the Pythagorean theorem and turns out to be 2.55 times 10 to the minus 2 newtons. Finding the angle, I take the inverse tangent of my y component over my x component, and it's going to give me minus 37.2 degrees because of the fact that I had a negative x component. if I look at my vector magnitude, I notice it has a positive y component but a negative x component, which means that my resultant force is in the second quadrant. So I'll take this angle and add it to 180 to get 142.8, which would be the angle measured from the positive x-axis. And so all that should look kind of familiar because it's the procedure for adding vectors using the components. But we did it with a new context, and that was with the vectors that we were adding were found using Coulomb's law.